Let's begin Unit 3, Lesson 2. Again, we're going to be graphing polynomial functions in this lesson, and we're going to look at a few models as well, maybe a few applications towards the end of it. So this lesson, we're going to highlight how to graph polynomial functions, and we're going to look at the models that can be used. And again, we're going to be interpreting data using the graphing tools of our graphing calculator. So again, steps to graphing a polynomial function. Some things that we were doing last time, we talked about end behavior. So remember, end behavior is identified by two things. The degree, if it's even, we said the end behaviors are the same. Either both ends are up or down. If A is positive, then both ends are going to be finishing up. If A is negative, then both ends are going to be finishing down. That three, if the degree is odd, then the end behaviors will be opposite. So if A is positive, the left side will be down, the right side will be up. If A is negative, the left side will be up and the right side will be down. That's that reflection that goes on. So again, remember, the degree is going to be determined by the highest degree of the actual polynomial function. Some of the things we'll have to do is we'll have to find the x-intercepts and y-intercepts. Remember, to find the x-intercepts, we're going to be setting y equals 0, and this is where we can be using factoring or graphing tools if necessary. There are some strategies to find the x-intercepts using our graphing calculator. To find the y-intercept, it's really not that hard because you're setting x equals 0, which makes the math actually fairly friendly to find the y-intercept. So he's usually not too hard to find. So remember, the x-intercepts are also called zeros. So this is where that multiplicity comes in. Identify the multiplicity of each number, each zero, and that's going to determine the behaviors at the x-intercepts. So at the x-intercepts, remember, if the multiplicity is 1, the graph is going to cross the x-axis. If the multiplicity is 2, the graph touches the x-axis. And again, it's going to be a minimum or a maximum depending on how the graph approaches the x-axis. If the multiplicity is 3, the graph is going to cross again, but it's going to be more like a snake. It's going to kind of flatten out. You also have to determine the maximum number of turning points. As I said, that's going to be 1 less than the degree of the polynomial. So once you know the degree of the polynomial, you subtract 1 from that, and that's going to be how many times the graph actually turns. So we're going to use this information in the graph, and to help with the scale of the y-axis. The graphing calculator can help us look at the table of the table in the graphing calculator can help us identify a few more points, and help us make a little bit more accurate graph. Again, especially what's happening between the x-intercepts, because we kind of know what end behavior is going to be. It's really what's going to be happening between those x-intercepts. So if I look at this problem here, if we want to find the end behavior, notice how we have an x squared and an x. That x squared times that x is going to give me this x to the third. So my degree is 3. And notice how the a is the coefficient of all the x's multiplied together. The a is going to just really be a 1. So since a is 1, we know that that's going to be enough information to determine our behavior. So again, if the degree is odd and a is positive, if degree is odd and a is positive, the right side is going to be finishing up and the left side is going to be finishing down. So our end behavior is going to be the left side is going to be down and the right side is going to be up. So as x approaches negative infinity, y will be approaching negative infinity. In other words, as the graph goes left, the graph goes down. As x approaches infinity, the y is going to be approaching infinity. In other words, as the graph goes to the right, the graph finishes up. As far as the x-intercepts go, since this is already factored, all we have to do is set each factor equal to 0. So we have this x equals 0 and x plus 5 is equal to 0. And therefore x would equal 0 still. That doesn't change. And then x equals negative 5. Now the multiplicities we'll pay attention to here in a second because that's going to be our next question. The y-intercepts we just set x equal to 0 and solve for y. So that's going to be y equals 0 squared times 0 plus 5. So that's going to be 0 times 5, which is going to be 0. So the y-intercept is also going to be 0. So the x-intercepts, as we said, are also zeros. So the zeros are, again, are your x-intercepts. So 0 and -5. Notice that the multiplicity of 0 is actually a 2, which means the graph is going to be touching there. And the other 0 is -5. And since it has a multiplicity of 1, that means it's going to cross. The turning points, since the degree was 3, 3 minus 1 would be 2. So the turning points would be 2. So no more than 2. There can be fewer turning points, but it cannot be more than 2. So if I put this all together, again, plotting some points, the x-intercept is 0. The other x-intercept is a -5. And the y-intercept is also 0. Okay. So from there, the end behavior kind of tells us that the left side is going to be finishing down. So it's going to be coming up this way to this first x-intercept. It's got to cross and then it's got to turn back around. And then since 0 had a multiplicity of 2, it's going to touch and then turn back around again and go back up. So our graph should take on that look there. And again, what happened between the x-axis, if we wanted to get a better graph, we would have to find a point in between there to get a more accurate graph. So let's see if our graphing calculator can help us out a little bit as well. So y equals, and if I clear that off, what do we say that was again? So I have x squared times x plus 5. If I hit graph, and notice that, my graph does go up quite a bit. So, but right now that's going to probably be enough information to get a good idea of what the graph looks like. And notice that it does have 1, 2 turning points as well. So it kind of matches the graph there. Okay, let's look at this next example. If I want to graph x plus 4 squared times 1 minus x. Notice how we have an x squared times a negative x. So this is going to be like a negative x to the 3rd power. So notice that a is actually going to be a -1 as well there. Since this x actually is negative, that's going to impact our a value. So our end behavior, again, it's a degree 3 with a negative. So if I go back up here, if a is negative, it's actually going to finish up on the left side and finish down on the right side. So my end behavior, it should kind of do this. So again, as x approaches -infinity, as I go left, y is approaching infinity, y is going up. As x approaches infinity, as the graph goes to the right, the y values are approaching -infinity, they're going down. So the x-intercept, since it's factored, we have this x plus 4 is equal to 0, and this 1 minus x is equal to 0. So x equals -4. Here I have negative x equals -1. Divide both sides by -1, the signs have to both change. So it's going to be x equals 1. By y-intercept, we have to set, again, this should be f of x equals this. So we should have y equals, and we're going to replace the x's with zeros, 0 plus 4 squared times 1 minus 0. So we're going to get 4 squared, which is going to be 16 times 1. So y would equal 16. So there is a different y-intercept this time. So the zeros are a -4, but also has a degree of 2. So its multiplicity is a 2. That means it's going to touch at that 0. And the other 0 was a 1. And since it has a multiplicity of 1, that's going to cross. And since the degree was 3, the turning points would be 2 turning points, because 3 minus 1 would be 2. So it's not going to have more than 2 turning points. That's the most turning points, maximum number of turning points. So if I put this all together, my x-intercepts are -4, 1, 2, 3, 4. My other x-intercept is 1. My y-intercept is 16. I'll just go by 2s. 2, 4, 6, 8, 10, 12, 14, 16. So my y-intercept is going to be there. As far as graphing now, the end behavior, notice how we said the left side finishes up. So it's got to be approaching this first intercept from this direction. And since that's a degree 2, it's going to touch and turn back around. It's got to go up here and cross through this y-intercept. Then it's got to come back down. And since it's a degree 1, it's going to cross and just finish in a downward direction like that. So that should be the shape of my graph based on that. So if we look at the graphing calculator, y equals, and clear this off, we have x plus 4 squared times 1 minus x if I graph that. And notice how it does kind of mirror my graph. The scale just doesn't go up high enough. But if I did change my window where my y max was maybe like 20, and if I go by 2s, I should be able to capture now that turning point up there. So notice that it does kind of turn, and it actually turned a little quicker than mine, but 1, 2, 3, 4, 5, 6, 7. I'm sorry, we'll go with 2s. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so notice actually went up a little higher. That wasn't the y-intercept wasn't actually a maximum there, but it was close to the maximum. But the -4 was a minimum point. Okay, so that's where the graphing calculator could get you a little bit more accurate graph. But again, all we have to do is get a little bit of the idea of the sketch at this point. If we want more specifics, then that's where the technology comes into play. So if I want to graph f of x equals -2 times x plus 5 times x minus 1 cubed, again, the end behavior, notice how I have an x and an x to the third here. So they have this x here raised to a power 1, this x raised to a power 3. X times x is x to the 4th. So, and my a is a -2. So if the degree is even and a is a negative, if I go back up here, if the degree is even and a is negative, they both should go in a down direction, both down. So end behavior should be down here and down here. So in other words, as x goes to -infinity, in other words, as x goes left, y is going down, or in other words, it's going towards -infinity. As x approaches infinity, as x goes to the right, we're seeing that y also goes to -infinity. So the left behavior is this first little notation, and the second end behavior is this notation. So basically what that's saying is they both finish down. So as we move into the x-intercepts, it's already factored for us. We just have to set each factor equal to 0. That's the nice thing about this, is we're not having to do any math at that point. So x plus 5 is equal to 0. So x is going to equal -5. And the other x-intercept, we have this x minus 1 is equal to 0. So x equals 1. So it's going to be my other intercept. So then we have our y-intercept. So to find the y-intercept, we set x equal to 0. So y is equal to -2 times 0 plus 5 times 0 minus 1 cubed. So y is going to equal this -2 times 5 and -1 to the third power. Remember, anything raised to the third power, the sign changes 3 times, so it's still going to be a -1. Okay, so I have -10 times -1 would be a +10. So my y-intercept is going to be a 10. As far as the zeros and their multiplicities, the -5 has a multiplicity of 1. So notice how it's going to cross at that spot. The other 0 is a +1 as well. I'm sorry, it's a +1, but the multiplicity is actually a 3. That's going to cross, but it's kind of going to be like the snake. It's going to kind of flatten out a little bit. The turning points. So since the degree is 4, 4 minus 1, oops, 4 minus 1 would be 3. So it's going to have 3 turning points at most. So 3 is the most turning points possible. So if I put this information all together, so one of the intercepts is -5, 1, 2, 3, 4, 5. The other intercept is at a +1. The y-intercept's at 10. So again, I'm going to maybe go by 2s. So 2, 4, 6, 8, 10. That's my y-intercept. Notice how on this graph, the end behavior is both down. So it starts over here. So it's going to come up to this 0. And since it's a -5, it's just going to cross without any fanfare. Somewhere along the way, it's got to turn back around. It's got to cross through this y-intercept. It's got to come back down, and it's going to have to kind of flatten out, kind of make a snake, and go on down. It should look something like that. So what we really don't know is what's happening between -5 and 1. If we want to get a little bit more specific, that's where we can use our graphing calculator to maybe find a few other points there if we need to. So speaking of the calculator, let's see what it gives us in this sense. So if I hit y equals and clear that off and put -2 in parentheses, x plus 5, close parenthesis, x minus 1 cubed. Let's see here, 3. If I graph that, notice how it does kind of do kind of what we did. I just don't have what happens way up here, but we do know somewhere up there, it has to turn back around and cross. Mine just doesn't go quite as far up, but notice how there's kind of, it's really even hard to tell where their y-intercept is because it's so steep coming across there. Notice how it does kind of snake at that 1 as well. So it does kind of mirror that. As far as turning points go, it really just has 1 turning point somewhere up there. It turns this 1 time, and that's about it. So just has that 1 maximum there. So again, it doesn't have to turn all 3 times. That's just the most number of times it can turn. So if I want to graph x times x minus x cubed, well, one of the things would be helpful is to put it in the correct order. So notice how this is actually going to be -x to the 3rd plus x. So notice how it's an odd degree with a negative there. So we know that the end behavior, the left side should be finishing up and the right side should be finishing down since a is negative. Okay, so the degree is 3 and a is negative. That's the behaviors. They are in opposites. So again, what this is saying is as x goes left, in other words, as x goes further and further left, -infinity, what y is doing is y is going higher and higher and higher. It's going up. We call that approaching infinity. Again, as x goes to the right, this is this other behavior. We're seeing x is approaching infinity. and y is actually going down. Y is going towards negative infinity. So that's kind of our end behavior. The x-intercepts, we have a little work to do here. So notice how we have this negative x cubed plus x. We have to set that equal to 0. What I like to do is I like to go ahead and factor the negative out as well. And there's an x in common, so I'm going to go ahead and factor out a negative x. Since they do have an x in common, and I'm going to go ahead and pull the negative out because I don't like my leading term to be negative. So that's going to bring out an x, so it's going to leave me an x squared. And since I pulled a negative out, that sign is going to change to a minus, and that's going to be a -1. So I have this x squared minus 1 is equal to 0. So what I have then is this negative x, and I have x squared minus 1, which is the difference of squares. So that's going to be factoring into x minus 1 times x plus 1 is equal to 0. So if you set each factor equal to 0, you have negative x equal to 0, x minus 1 equal to 0. Oops, went too quick again, because I was already seeing the answer there, x equals 1, but I'll slow it down a little bit. So x minus 1 has to equal 0. And then x plus 1 has to equal 0. So if you divide both sides by -1, that's just going to give you x equals 0. Add 1 to both sides, x equals 1. Subtract 1 on both sides, x equals -1. That's going to be your x-intercepts. So 0, 1, and -1. As far as your y-intercepts go, we set x is equal to 0 now, so y equals then, and we replace x with 0, so we have 0 minus 0 cubed. That's just going to be 0. So it's actually easier to do the y-intercept when it's expanded out. So it does make that easier, but it doesn't make the x-intercepts easier. So the zeros are a 0, a 1, and a -1. And all their multiplicities are 1. So that means every one of these, the graph is going to cross each time. The turning points, if the degree was 3, 3 minus 1 is going to be 2. So there's going to be at most 2 turning points. So if we sketch this graph, we should have 0 is an x-intercept, -1 is an x-intercept, and 1 is an x-intercept. The y-intercept is 0. As far as end behavior goes, notice how the left side finishes up. So it has to come down. It's got to cross. It's got to turn to go through that x-intercept. It's got to turn again to go through that x-intercept. And then it's just going to finish down. So it does have 2 turning points in the graph. So if we take a look at that graph on the graphing calculator, we clear that off. We have x minus x cubed, your graph. And notice how it's really hard to even see it. It's so close there. It turned a lot tighter. So there's the 1, there's the 0, and then it came up above, barely above the x-axis and came back down through there. Mine was a little bit more pronounced than theirs, but it kind of gives you the same typical graph there, very similar in the shape. So if I want to graph 2x to the 4th plus 12x cubed minus 8x squared minus 48x, that's a handful. So to start with, though, we have end behavior. Notice how the degree is a 4. And A is a 2. So that means since the degree is even, they both finish the same direction. And since A is a positive 2, that means that both sides are going to finish up. So the left side is going to finish up somehow, and the right side is going to be finishing up. So again, what this is saying is as x goes to the left, as x approaches negative infinity, as x goes left, your y's are going up, or y is approaching infinity. And then we have as x approaches to the right, infinity, your y's again are approaching up, they're approaching infinity. So we use what we call some limit notation. So you'll see a little bit more of that if you take calculus. So the x-intercepts, we have to set this polynomial to 0. So we have this 2x to the 4th plus this 12x cubed minus this 8x squared minus this 48x. Since there's 4 terms there, we can factor by grouping. So remember when I factor by grouping, I kind of use a box. So I kind of box these first 2 in, and I box these second 2 in, and we'll hope for some luck here that this actually will somewhat factor for us. So once we do that, we find the GCF of the first 2 terms. So they have 3 x's in common. So an x to the third is going to come out. I can also pull out a 2. So 2 comes out. So 2x to the third comes out. That's going to leave me an x and a 6. When there's a negative here in this position on the second piece, we pull the negative out as well. And they both have an 8 in common. So negative 8 is going to come out. So if this here, a minus 8 comes out. And then we have then an x also can come out. And then we have x minus, or actually the sign changes to a plus 6. So now what I have is 2x cubed minus 8x times this x plus 6, since that x plus 6 is in common. Notice this first front piece has a 2 in common. It also has an x, so I can pull out a 2x. I probably should have pulled the greatest common factor out to begin with. I just missed it. I got it there though. So if I pull a 2x out, that's going to give me an x squared minus 4 times x plus 6. So now the x squared minus 4 actually is factorable. So it's going to be a 2x, x minus 2 times x plus 2, since that's a difference of squares, times then this x plus 6. So we set each factor equal to 0. So we set 2x equal to 0, x minus 2 equal to 0, x plus 2 equal to 0, and x plus 6 equal to 0. So 2x equals 0, that's just going to be x equals 0. This is going to be x equals 2. This is going to be x equals negative 2. And this is going to be x equals negative 6. So your x-intercepts, there are 4. 0, 2, negative 2, and negative 6. Okay. To find the y-intercept, I set x equal to 0. So if you set x equal to 0, this is going to be 2 times 0 to the 4th plus 12 times 0 to the 3rd minus 8 times 0 squared minus 48 times 0. And remember, when you're multiplying by 0, all that just turns into zeros. So this just turns into 0 because you're multiplying by 0 in each one of those. So the multiplicities and zeros. So again, there are 4 zeros: 0, 2, negative 2, and negative 6. And since they all have a multiplicity of 1, we know that the graph is going to cross at each one of those zeros. The turning points, 4 minus 1 is actually going to be 3. So at most there's going to be 3 turning points. So if I sketch this, we have a negative 6, 1, 2, 3, 4, 5, negative 6. We have a negative 2. We have a 0. And we have a 2 are my x-intercepts. My y-intercept is 0 as well. Now my end behavior, notice how it finishes up on both of those. So it's got to start on the high left over here. It's got to cross through this x-intercept. It's got to turn to pass through this x-intercept. It's got to go up and turn again to pass through this x-intercept. That's got to turn again to pass through that x-intercept. So it kind of takes on that look. So that's kind of a rough sketch of the polynomial function. So if we graph this, see if we can have some luck there. We have y equals, and we clear this off. We have 2x to the 4th plus 12x cubed minus 8x squared minus 48x. Hit the graph. Notice how it kind of does its thing. Notice how on the far left, it's just much steeper than mine, but it crosses through that x-intercept of 6. It turns down here somewhere, comes back through -2, goes up really high again, and comes back through to the 0, turns back around and goes back up. If I want to get a better look at the graph, I'd probably have to change my window where my y values were much larger and smaller. So if I make my y min maybe a -100 and my y max a positive 100, if I go by tens, I may get a better look at the graph. Yeah, that would be a much better sketch of the graph. I'd still have to go much further down in my y's. So I change my window again and maybe make my y min maybe a -200. In doing so, I may want to, so I need to break that -200. I think I'll probably put a fraction in it. I probably need to go by like 25 or something in my y scale, so there won't be so many tick marks. So if I hit graph again, notice how I got pretty darn close to getting the whole graph, or at least the important pieces of the graph seen as far as those maximums and mins. And notice how we do see this. There are 3 turning points. One down here that we can't really see yet. There's this one here, and then it turns again. So there are 3 turning points in the graph. Now, on this one, if you wanted to find your x-intercepts, we can use the graphing calculator and find what's called zeros. So if I go back to that briefly. So if I had a hard time finding the x-intercepts, what I could have done is graphed it and where it crosses the x-axis. And notice how, since the degree is 4, there can't be more than 4 x-intercepts. So we see 1, 2, 3, 4 of those x-intercepts. So we know we found them all. If you hit the second button and hit the trace button, it'll do what's called calculate above there. And number 2 is called a 0. So 0 is the same thing as an x-intercept. So if you hit that, notice how if you want to find that one, you just hit enter, and hit enter, and it takes you, whoops, I didn't go far enough left or right. Whoops. Try that again. Second, calculate. Let's just go ahead and go out to the far left here. We'll just work our way from left to right. So the left bound means I have to be left of the x-intercept. So you have to actually be above it over here, hit enter. The right bound, in this case, you actually have to be to the right of that spot. That looks pretty good. Hit enter again. Hit enter again, it'll take you, and that will be your x-intercept to -6. So if you didn't want to do all this factoring, you could be using the calculator to maybe find those zeros. And as long as they're nice, clean, whole numbers, you would be getting your y-intercepts without actually having to do the factoring. So keep that in mind. I could do that for each one of those. So let me try to do one more. So if it's second, calculate again, hit number 2 for zeros. If I move to that next x-intercept, notice how it says left bound, so I need to stay underneath here to start with. Hit enter. And then I have to be to the right of it. Notice how that mine gives me these little nice style lines here. Hit enter. Notice how that is to the right of the x-intercept. Hit enter again. Notice how it does take me at this -2. Okay, so you can use your graphing calculator to find the x-intercepts by using the 0 function on your graphing calculator. So let's graph the polynomial function using the graphing tools of your calculator. So first off, though, in behavior, we really don't need the graphing calculator. We should know that the highest degree is a 3. And since a is a 1, so the degree is 3 and a equals 1, we know that one side finishes, the left side has to finish down, and the right-hand side has to finish up. So in other words, as x approaches -infinity, as x goes left, the y's are approaching -infinity since the y values are going down. Again, as x goes to the right, this is this other behavior, other end behavior. As x goes to the right, x goes to infinity. The y values are going up, so y is approaching infinity. So it would be my end behavior there. The left side's finishing down, the right side is finishing up. So if I want to graph this on the graphing calculator, so y equals, and clear this off, and we put in this x cubed minus 2.91x squared minus 7.67 x minus 3.82. So if I hit the graphing button, we can kind of see our graph. And notice that the degree is 3, so we know that we're looking for at most 3 x-intercepts. And we kind of see there's one here, and notice how it touches. So it has actually a multiplicity of 2, and there's one over here somewhere. So let's see if we can find those two zeros, if we will. We'll see if this actually does it or not. This might be a tricky. We'll see what we can do here. So second, calculate number 2 for zeros. So if I do my left-hand behavior, if I go to the left of that, hit enter. If I go to the right of it, hit enter, and then hit enter again. So it's looking for a sign change, so it doesn't like that. Well, if I go back to the graph, well, we also pick up on that this would be a local high point or a maximum. So instead of using the 0 button, I could use the maximum button for that. So hit the second, calculate, since that's more of a maximum anyway. We hit enter there. We do the same thing, a left bound here, a right bound over here, hit enter again. It does take us to our maximum. So our x-intercept is going to be basically like negative 0.9. So one of the x-intercepts would be, x is approximately negative 0.9. And if I go over here to this other x-intercept, and again, since it does have a sign change, I can use the 0 tool to do that. So if I hit the second, calculate number 2, we'll find a 0, because that's not really a maximum or a minimum. Come over here, and I have to be a left bound first, so I have to be to the left of that x-intercept, hit enter. Then I have to have a right bound, so I have to go to the right of it. That looks pretty good. Hit enter again. And my other 0 is like 4.7 if I'm rounding to the 10th place. So the y-intercepts, only way to find the y-intercept is you have to set x equal to 0. So what we can do here is, if I go to second and hit table set, what I can do is I can change my independent variable to ask. If I do that, I can input, it'll actually put the 0 in for x for me. So if I go second and hit the table now, if I put 0 in for x, it'll give me my corresponding y value of negative 3.82. So that's going to be my y-intercept of negative 3.82. Now remember, I never changed my window, so that's why it looks kind of strange there. Because if you look at my window, I never really changed these values. If I go back to zoom and hit number 6 for standard, you can kind of see that, yeah, that actually looks closer to -1 there. And 1, 2, 3, it's right close to 4 for the y-intercept. And the other x-intercepts are at 4.7, so that's between 4 and 5. 1, 2, 3, 4. That's looks pretty darn close there as far as that goes. So remember your window to go back to a normal standard window where it's just, -10, 10, 1, -10, 10, just to those basic tick marks, you have to hit numbers, you have to hit zoom and number 6 to get back to the standard window. Okay. So if I want to use the graphing calculator, I can now kind of sketch the graph as well by hand if I want to. So we have so there's -1 here. So -0.9 is going to be about here. The other x-intercept is 4.7. 1, 2, 3, 4, 5. 4.7 is going to be between 4 and 7, closer to 5. -3.82. 1, 2, 3, 4, and that's going to be closer to, or yeah, I could have probably rounded that to about -3.8, around there. The end behavior, notice how it finishes down and up. So the graph has to kind of start down over here. It's got to cross through here. It's got to turn around to get to that y-intercept, and then it's got to turn around somewhere and go through that other x-intercept. So the graph has to roughly look something like that. Okay. So the turning points, there should be no more than 2 turning points. We do see 1. We do see 2 turning points here. So if I want to draw the graph by hand, that's kind of what I just did there. There's my rough graph by hand. If I want to determine the range, my range is, notice how the behavior on the range is lower bound and upper bound. Notice how this arrow here is your lower bound and this arrow here is your upper bound. So the range really goes from all the way down to all the way up. So everything's included in the range. That's at -infinity to infinity. So where is the function increasing and where is the function decreasing? So remember, it's increasing. Let me see here. Did I miss an x-intercept? I think I've only got 2. I should have 3, shouldn't I? Oh, I know what happened. If I look back at my graph, we see that this actually was a degree 2 multiplicity. So that's where I probably need to clean my graph up a little bit. Oops. Try that again. Let's just clear that all off. So if I get my eraser out, I try to sketch that graph again. We do have this touch here where it turned, it didn't actually cross, then it turned, and then it kind of went back this way. So where it's increasing is where the graph is going up. So from left to right, we kind of see from here to here, the graph is going up. So looks like it's going to be increasing from -infinity to about -0.9. But also notice how it's somewhere around here, it's turning. So to find the other one, I really need to find this turning point over here a little bit more so. So to get the other interval, I really need to find that other, that local minimum. So if I hit the window, I really need to change my y min to be a lot bigger. So let's say like -200, and let's go by 25s again. See if that got my graph on there. Yeah. So notice how now I have this little local minimum that I would have to find. So to find where it's increasing, that's where that turning point happens. So if I hit second calculate, if I go and find that min, number 3, my left bound would be somewhere close to it. Hit enter. My right bound just be on the other side of that. Hit enter. Hit enter again. And notice that spot over here somewhere is where it actually is turning again. So somewhere around there is where I should have, maybe I have to regraph this one more time. Let's see here. So if I was sketching that, so notice how 2.84 negative 20, it's going to be down here somewhere. So negative 2.8 is going to be about here. So if it looks like this graph kind of does more of this, it comes up here, it crosses or touches and comes back down. It crosses through that x-intercept, then it has this turning point here and goes back up. So that's what my scale would be roughly. So this was around negative 2.8. So from negative 2.8, so negative 2.8 to infinity, to positive infinity, would be the other increasing interval. Where it's decreasing between this x-intercept and where it turns down here. So it's decreasing from that negative 0.9 to that negative 2.8. That would be its decreasing interval. And again, you could use a bracket on each one of these if you want, or parentheses. It doesn't matter in my lab math. If you like to use those brackets for that, that's fine. So up here, even if you want to use brackets here for that, you can, but it accepts parentheses or brackets here. So I'm used to doing brackets actually. So that's why I kind of changed that. All righty, so what else do we have here? So we have an application. So cubic function scatter plot and a best fit equation. So this looks like a job for the calculator as well, but let's see where we're going with all this. So hurricanes in 2012, Hurricane Sandy struck the east coast of the United States, killing 147 people and causing an estimated $75 billion in damage with a gale diameter of about 1,000 miles. It was the largest ever to form over the Atlantic Basin. The accompanying data represent the number of major hurricane strikes in the Atlantic Basin that were category 3, 4, or 5 each decade from 1921 to 2010. So from 1921 to 1930, in that decade, there were 17 hurricanes reported. They're just going to use one to represent that decade. 1931 to 1940, we're going to use the 2 for that decade, and 16 hurricanes were reported. So we kind of get the idea of our information here. So notice how it kind of starts, it goes up, it peaks out, it goes back down, if I'm looking at the Y values, and then it kind of goes back up again. So it looks like it's got like 2 turns in the data. It kind of goes up to 33, turns back down, and then it's increasing again. So let's draw a scatter plot just using this by hand. So 1 would be 16. So 1/16 would be about here. 1/17. So let's see, then we're going by, so let's make that a little bit higher. So we're going by 3s on my scale. So 3, 6, 9, 12, 15, 18. So 17 is going to be a shade under that. So the next one we had was 2/16. So it's going to be a shade under that. So 3 would be 29. So 29 is going to be, so that's 27, that'd be 30. So 3/29 would be, about here using my scale. 4 would be 33. So 4/33 would be here. 5 would be 27. So 5/27 would be here. 6 would be 16. Out here. 7 was also 16. And then 8 was 27. And 9 was 33. So you kind of see the data does kind of make kind of a two-turn, or a lot of times we refer to it as like a third degree, at least a third degree function. So let's use the TI-84 to find the cubic function that fits this data. So I'm going to go ahead and turn my scatter plot back on as well. So second stat plot, and I have to turn number 1 back on. So I hit enter. I'm going to hit enter again to turn that back on. Now we can go to stats. We can hit enter to edit our data. Let's clear off the old data. So we got 1 through 9 here. Okay. Here we have 17, 16, 29, 33, 27, 16, 16. Okay. So in order to do a stat plot, we hit zoom, and number 9 will do the shortcut to fit the data there. Notice I have a graph already on there. So if that y equals and clear that graph off and go back to the graph. Notice that their scale is different than mine. If I made their scale like mine, so if I said my window was, if I said 0 is max min, and I went to 35, and my X scale, if I make that go by, I'm sorry, this is the X min would be 0, the X max would be 10, going by ones. On the Y min, we say 0 to like 35. But if I change that to 3, now I go back to graph. Notice how the data now mirrors mine a little bit better because I make the windows look the same. So to do a cubic line of best fit, we use the stat button. And remember, the calculate is where those menus are, those regressions. Remember, 4 was the linear regression, 5 was the quad regression, 6 is going to be the cubic regression. And notice how we don't have to change any of this data here. We just move on down to calculate. And then we can enter our line of best fit. A lot of times the calculator requires us to do like maybe on my lab map, maybe 4 decimal places. So if I'm using 4 decimal places, I should have now, my new function is going to be f of x equals 0.3948. Let's see here. And that's going to be x cubed. Plus then your b is, so it's going to be a minus actually. So minus 5.9563. That's going to be x squared. Plus 26.1965 x, and then your d is going to be a negative, so a minus then 7.4127. So if I want to let the calculator graph that, we can then type it in if we want. Or actually, we don't have to graph it necessarily, or do we? Yeah, it does say do this. Let's see what this first question is before I move on. So use the cubic function model to predict the number of hurricanes that struck the Atlantic Basin between 1961 and 1970. So if I do that, what I pick up on is 61 to 70 is where that 5 is. So what I need to do is put a 5 into this equation. So I'm going to go ahead and put that equation to my calculator. So 0.3948 x to the third power minus 5.9563 x squared plus 26 point x minus 7.4127. So what I'm going to do to evaluate when x is 5 is I'm going to let the calculator do it through the table set button. So if it's the second table set, notice how my independent variable is ask. That's what I want. I want to keep that as ask. So if I go to the table, second table, I can go ahead and clear that off or delete that, whichever goes first here. Let me see here. So let's go ahead and, all right, we'll just type over it. So we got what, a 5 going in, hit enter, and that'll give me 24.12, so about 24 hurricanes. And so if we look at the data, that said 27. So we're kind of close to predicting there. So that's working pretty good. So use your TI-84 to draw a scatter plot. I think we've already done that, and the line of best fits. So since I wrote the equation there, it should do both now. That graph, notice that that's your graph. It kind of does that. So it looks like it only has one x-intercept, and then it just kind of keeps gradually going up, but it does have a local maximal and a local minimum in that. So let's see here. So we did that. So concern has risen about the number of hurricanes and intensity. Some scientists believe this just a natural fluctuation that could last another decade or two. Use the model to predict the number of hurricanes that will strike the Atlantic Basin in 2011 and between 2011 and 2020. Is your result reasonable? So 2011 and 2020 would be actually using the value of 10, because 9 would be 2001 to 2010. So we're going to be evaluating f of 10. To do that, I'm going to let the calculator do that. So again, notice how under my table set, independent variable says ask. So all I got to do is go to the graph. And if I go up here, I think I can clear that off. We don't want to clear that off. So let's see here. Hit delete. There it goes. It made it go away. So if I put a 10 in place to that, hit enter, it should give me that. 10 would be 53.7. So if I round that, it'd be like 54 hurricanes. So based on that, if you look at your data, it does look like it's on this upper trend right now. So how far that upper trend goes, I don't know, but looking at our graph again, where x is 10, it is kind of peaking up here rather quickly. So what does this suggest about the reliability of using a model to predict an event outside the domain data? Well, my looking at this, that's actually not a bad prediction. So I would think, as long as you don't go too far out, it's somewhat reliable. So it can be used. So I would say it can be reliable to a certain degree. But again, the more data we have, the better our predictions are. But notice that, 1921 to 2001, we got to take in a lot of things that go on there. One is what we've done as human beings to affect our climate. There is this discussion of global warming going out there. So is global warming really impacting hurricanes, or is this just kind of a natural fluctuation? Right now, the data probably says right now it's more of a natural fluctuation based on the data. But there would be some flags to be concerned about because these are predictions. These are not hard facts. So this is just an educated guess. So we have to keep that in mind as we move forward, that it's only an educated guess. All right. So that concludes this lesson as well, of trying to put polynomial functions into graphs. So we went from the equation to the graph using the characteristics of polynomial functions. So I will close there. You all have a good day.